Okay, so in this case, we want to determine whether the following equations are exact. If they are, if not, want to find the integrating factor and find the solution. So here we won't go all the way to find the integrating factor. All we want to see is we want to solve exact differential equations. So we'll restrict ourselves to the ones that are exact in finding how to solve them. So let's start. We can go through all of them as we try to see which ones are exact and which ones are not. So let's get the first one. We have 1 plus y e to the x plus xy e to the x, and then this is dx, then plus x e to the x plus 2, and then we have dy there is equals to 0, and then this is giving us that initial value problem. So is this exact or not? So here, of course, the coefficient of dx, that is going to be our mx comma y. This is 1 plus y e to the x plus x y e to the x. So, and then our n, function of x comma y, that is going to be x e to the x plus 2. So to check if this differential equation is exact or it is not, so we get partial m, partial y. So with respect to y, this is going to be a 0. This part here only has a y here, so this is just going to be e to the x. The partial derivative here with respect to y is just going to be 1 plus this side. Also, y only shows up with this term, so the derivative there with respect to y will just be x e to the x. So this becomes partial m, partial y. Now let's check partial n, partial x. In this case, with respect to x here, we see that these two terms both have x and they're multiplying. So I'm going to differentiate by product rule. So we'll keep x, differentiate e to the x, and that will remain e to the power x. Plus, now we'll keep e to the x and differentiate x, and that will just be e to the x multiplying 1, since the derivative of x with respect to x will be 1. So we are done differentiating this by product rule, and it has reduced to give us this. Next, we differentiate 2 with respect to x, that will just be 0. So we remain with this as the solution. Now, is our differential equation exact or not? Let's compare. Is partial m, partial y the same as partial n, partial x? Are they the same? Let's see. E to the x plus x e to the x. E to the x plus x e to the x. Yes, they are. So it is exact. So this one is exact. So we'll see how best we can work it out now that it is exact. But let's check what else is exact here. Let's go to b. And for b, we have x plus 3 x to the power 3 sin y dx plus x to the power 4 cos y dy is equals to 0. Tell me whether each of the following equation is exact. If not, find the integrating factor, then find the solution. So looking at this, the way the question is being phrased here, I think they're trying to, they want us to find which ones are exact. And for the exact ones, we can still go ahead and find the solution. But looking at this, if not, find the integrating factor. Regardless whether exact or we need the integrating factor, in the end the statement is clear for both parts. Find the solution. Okay, so let's check B, if B is exact. So this is what we have. And in the same way, we define M, x comma y. This is x plus 3x to the power 3 sine y. Let's get partial m, partial y, and this will be 0. Here, the 3x to the 3, that's just a constant. Since that's just only x is present there, so that will just differentiate the sine y there. That will just be cos y. Next, n, and this will be x to the power 4 cos y. We get partial n, partial x. So this will be the 4 multiplies down here, x to the power 3 cos y. Now when you compare the two, partial m, partial y, is it equal to partial n, partial y? Well, this one has a 3 here, this one has a 4 here. Based on that, the two expressions are different. Did I copy them wrongly? Yeah, this one is x to the 4, and this one is 3x to the 3 there. So yes, the two expressions are not the same, so not exact. So for this one to work it out, we'll have to find the integrating factor. We can do C as well. So for C we have 2xy squared plus y dx plus 2y cubic minus x dy is equals to 0. Is this exact or not? So I hope at this point you're getting the trick, the hang of it. Checking whether it is exact or not is the straightforward part. Perhaps the only tricky part is working it out, but as well just routine on solving if it is exact or not. So define m. So we have 2xy squared plus y. Define n. And then we have 2y cubic minus x. Get partial m, partial y, partial m, partial y. So y is the variable, so the 2 multiplies to give us 4x. Y remains power 1. This is y, so that will just be 1 here. Let's get partial n, partial x. The 3 multiplies, this is a y. So if you say to x, that is a constant, so that is just going to be 0 there. And then we differentiate here, that is just going to be minus 1. So here we see that partial m, partial y is not equal to partial n, partial x. So I hope you've seen how we check whether it is exact or it is not exact. This one is not exact. So we only found one which turned out to be exact, which was this one. Okay. So if it turns out that a differential equation is exact, then how do you work it out? For this one, we were given the initial value condition there. I want to work it out without the initial value condition, but we'll keep it somewhere close just in case we want to use it. But let's solve it generally so that you understand the tricks we were illustrating earlier on. Okay, so we have this as our m, and then we also have this as our n, x e to the x plus 2 and so on. Okay, now for the next part, in terms of how you proceed from here, this is our m, this is our n. You want to keep in mind that to get m, you had to get the partial derivative of the original function f with respect to x. This is what actually gave you m. And to get n, you had to get the partial derivative of the original function with respect to y. This is what gave you n. Now the first step here, completely up to you, but you want to try to simulate this and try to see which one would be easy to integrate here. So which one would be easy to integrate here? So would it be easier to integrate it if you started by picking this one? Would be easy to integrate this one with respect to x, or would it be easier to integrate this one with respect to y? So I want you to look at the two expressions very well. Which one is easier to integrate? Since this is partial f partial x, so you'll be integrating with respect to x. So is it easier to integrate this with respect to x, or is it easier to integrate this one with respect to y? Which one is better? Which one is easier? What do you guys think? It's easier to integrate the second one with respect to y. Okay, so based on that, we can proceed and see how we can integrate that. You can still try to get the first one and see how it will reduce, but it's just a matter of which one is easier to work with. You can get this. Once you see that it's seemingly complicated, very quickly try the other one and see if it will be easier. So I'll get this one. So we'll say, okay, partial f partial y is equals to n, and n is this e to the x plus 2. So from here, let's see how it proceeds. We see that partial f is equals to x e to the x plus 2 partial y. We perform the integral. We have f, a function of x and y, equal to, so since it's with respect to y there, we'll introduce a y at every time. xy e to the x, this is another constant, so it's going to be plus 2y there, and then plus a constant h. But since we're doing it with respect to y, we're integrating with respect to y, we know to say that our h here must be a constant that depends on x. So that constant must depend on x. Now, what is this constant here? To understand exactly how that constant looks like, we recall the other expression, that when f was differentiated, but this time with respect to x, the solution was m. So let's start, since we have a rough picture of how f looks like, let's differentiate it. So when you differentiate this rough picture of f with respect to x, here we see that we have to do it by product rule. So first I'll keep xy, differentiate e to the x, I'll get e to the x, plus, now I'll keep e to the x, and differentiate xy with respect to x. When I differentiate xy with respect to x, the solution will be y. I hope you are able to follow that product rule differentiation there. So that concludes the partial differentiation of that expression with respect to x. Then it comes to this one with respect to x, it's 2y, so meaning with respect to x that is a constant. So we go straight to that one. That is h of x. With respect to x, it's not a partial differentiation. This is going to just, this will depend solely on x. It's just going to be dh dx. But we know the partial f partial x is actually equals to m. Meaning this xy e to the x plus y e to the x plus dh dx. In place of m, we can get back what m is. M is this. So you can put this where we have m. From here, everything else, since this is dh dx, key thing is this is dx. Everything else that has a y must cancel out at this stage if you've done it correctly. Let's see. X y e to the x, it's here. It's also present here, and they're both positive, meaning when you group them on one side, they'll subtract out. This one goes. This term also has a y e to the x. Guess what? Then this one, y e to the x, occurs there. Same sign, when they group, they'll subtract out. So now we remain with only dh dx is equals to 1. This is what we remain with. So from here, we can easily figure out what h is. When you integrate both sides, you see that h will be equal to, since this is just dx, so it will just be h. Of course, you're integrating both sides, so this will be h. And here, since we are doing it without limits of integration, we have to introduce a constant. Now, this constant will not have a variable, it will just be a constant c. So now we know that h, a function of x, is equals to x plus c. So this is what our h is. So we can now get our solution, our rough solution that we had. But since we now understand what h is, where there's h, we can put that solution. H is x plus c. Now, this is fine in most cases, but they gave us a condition. What was the condition? The condition in the problem, which is this one, y of 0 is equals to 1. Now let's find it in the problem. Y of 0 is equals to 1. So, what does that actually imply? Here, they're telling us to say, where is that? Okay. Okay, so where is that? Y of 0 is equals to 1. Okay, so the weird part is here, this is, they're using one of the variables here. And they're saying this is equals to 1. But generally, how this one would work here is, the condition here is kind of defining when x is 0 and y is 0. Then the solution would be equals to 1. In other words, here I'm just generalizing on how mostly it will be given here. It's a way of helping you figure out what this constant here is. So they would tell you what the function, what the solution would be if x is something, a given term, and y is a given term. So let's say they are saying f of 0, 0 is equals to 1. They're giving us the initial condition. So if f of 0, 0 is actually equals to 1, what do we do? Then we can say that, okay, if x is 0 and y is 0, then where there's x, we put 0. This whole thing would be 0. This would be 0. And this would be 0. Meaning, would only remain with c here. But they're saying f of 0, 0 is equals to 1. Meaning c must be the one equals to 1. Implying that this expression, since we now know from the initial condition, we now know that c is 1, we can now bring it here, and where there is c, we can now place a 1. So this now becomes the final solution. So this is what we end up having. Any questions here?